Hello and welcome to another video. In this video we're going to be working on the minimum number of operations to make XOR equal to k. And this one you have a array of numbers and an integer k. And you can take any number and flip any of its bits from a 0 to a 1 or vice versa, and that counts as one operation. And you can also do this with leading zeros. And you want to figure out the minimum number of operations to make the bitwise XOR of the whole array equal to k. So if we take a look at this first one, what they did is they flipped 3 and they changed it into a 2. So if you change 3 into a 2, it's going to look like this. And then they take the 2 and they turn it into a 6. So it's going to look like this. And then the whole thing is 1 now. So the other two numbers are 1, so 0, 0, 1. And the last number is 4, I believe. So this. So if you XOR all of this, you get 1, 0, 0, which is 1. Yeah. So in the second example, you don't need to do anything because the XOR of this whole thing is 0. So the basic thing you need to know is for XOR, like if you XOR a bunch of numbers, what determines the result? Right. So if I XOR like, we'll just have some numbers. This, whatever. Like let's say XOR all these. What determines the result of each bit? So XOR basically all it does for each bit is you just have, do I have odd or even number of ones for the bit? And so here we have even. So even will give you a 0. So if you XOR all these, you get 0. Odd will give you a 1. So 1, 0, 1. And that's basically all you need to know for this problem, and then it becomes kind of easy. So all you do you could kind of do this in two ways. You can actually go through every number and like count, maybe make like an array of something of, like the bit and then the total count for every single number added together. So you could say like, if I have an array of, every single bit of the number, let's say I have like the 0th bit, the first bit, the second bit, and so on. And then you can have a count here. So you could say like this, the total here is 5, 4, 3, whatever, like this. And then you can also do that, and then you can figure out like, okay, well, what's the bit of the k? So if the bit of the k is 1 here, and this is odd, I don't need to do anything, and so on and so on. But this is a little bit more confusing, so I wouldn't recommend doing that. So instead, what I would recommend is just XORing everything and getting a result. So once you XOR everything and get a result, and so let's say this is what we get, and then let's say k is this. All we really need to do is figure out how many bits have like a different bit, and then to change one bit in here only takes one operation, because remember it just tells you like for every bit it's just, do I have an even or odd number of ones? So like if this is a 0, all I have to do is add 1 1 anywhere or remove 1 1 anywhere. You don't really care like what number you're changing. All you're asked to do is figure out how many operations you're doing. So if I want to change this into a 1, I can either take one of these and turn it into a 1. Now I get a 1, which is one operation. Or I can take one of the ones and make it a 0. And because you can either change a 0 or a 1, you'll always have an available bit to change. Like you're never going to have a case you don't. So all you really need to do is just get the XOR of all your array and then compare it to k. And then for every single bit there's a difference. Just add 1 to the result. So like here, your result will be 2. Because I need to change a bit here and a bit here. And there's a bunch of ways you could do it, but like I said, you don't really care about how do I do it, you just care about the number of operations. And you know that to change one bit in the result takes one operation. All I have to do is just change any bit in any of these numbers to the other one. So like I said, I can just do like this as one operation, and then I also need to make this a 1, so I could do like this as one operation. And now I have odd, 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 odd. So I'll have this. Now there's also an easier way to do this part as well. Instead of like comparing these, what you can do is, so if the numbers are exactly the same, like if you have k XOR k, this will be 0. And if the numbers are different, so let's say this is k, right? This is k. This is your original number here. So look what happens when you XOR them. So if I have 1 0 1 0 XOR 1 1 1 1. Let's actually draw them to make it easier to see. So 1 0 1 0 XOR 1 1 1 1. So I get 1 0 1 0. And remember, it just like the bit just counts the number of ones. If the number of ones is odd, it's a 1. If it's even, it's a 0. So here, this is what we have. And notice that all the ones are the positions where the bits were different in the original two numbers, right? So here and here, there's a difference. And here, there was a difference. And this is always going to happen because for XOR, XOR of 0, 1 equals 1, XOR of 1, 0 equals 1, and XOR of 1, 1 equals 0, and XOR of 0, 0 equals 0. So the only time you get a 1 is when the bits were different for two numbers. So it'll basically tell you, like, okay, anytime I have a 1, when I XOR my result in k, I have a bit that I needed to change. And the total of these ones is the number of operations I needed to make, right? Because I didn't need to change these two bits. So that's kind of how you can do it. You can XOR your entire array, get a number, XOR that with k, and then every single one means there was a bit I needed to change in my array to make it equal to k. And that's basically it. And then, so this part, if you haven't done too many bit manipulation problems, if you want to figure out the number of 1 bits in a number, I think there's a built-in function, but also what you can do, there's a few ways, but essentially one of the easier ways is you can just keep anding your number with 1, or you could divide it by 2. So like this number starts off being, 5. So if you keep dividing your number by 2, you'll check if this last bit is a 1 or a 0. And basically what you do is, or you can AND it with a 1. So if you AND these together, and you'll get a 1 if this was a 1, and you'll get a 0 if this is a 0. So that's what I'm going to do. So basically you AND it with a 1, and you say, okay, this is a 1. So then if it's a 1, I add 1 to the result. Then I'm going to get rid of the last bit, and you can do that by shifting your number to the right. So shifting your number to the right just means getting rid of this, put a 0 over here. Then you AND this with a 1. This is 0, so don't care. Shift it again. Now AND this with a 1. I get a 1, so add 1 more. Shift it again. And now my number is 0. So you just keep doing this. You keep ANDing your number with a 1, and you keep shifting it to the right. Or dividing by 2. Either one works. So like if you have 5, for example, if you do 5 divided by 2, I think it's like a floor divide. So you'd get 2. And that makes sense because 5 is like this. So if I shift it to the right, I'd get this, which is 2. So I'd get 5, and then it'll go to 2, then it'll go to 1, then it'll go to 0. And my result will be 2. But yeah, that's pretty much it. All you really have to know for this problem is what determines the XOR bit is just, do I have an odd number or even number of ones? Because every 2 ones will make a 0. So that's why you have to have an odd at the very end. Yeah, so we can code this. So once you kind of get that, like there's a lot of ways to make this like super easy to code and super easy to understand, hopefully. So essentially, so first we're going to take every number in nums and just XOR them all together. So we can say like int XOR, start it with 0, and then we'll XOR that with every number in nums. And 0 XORed with the number just gives you that number. So we can say for int. And if you're not too used to bit manipulation, there's a bunch of bit manipulation problems. So just do a bunch and you'll learn all these like XOR tricks and all this stuff. So I've done a billion, so like it's pretty straightforward. But if this is still kind of confusing, you can always ask me as well. But yeah, just do a bunch of problems with bit manipulation and it gets pretty easy. So by the way, so XOR in most languages looks like this. So equals XOR. So this is the XOR operation. So this will XOR the two numbers. Like bit by bit. You can also, there's a shortcut way to do it, which is like this. So this is the same thing as like, and equals for and so on. So you can do this with XOR, you could do this with and, you could do this with or, I believe. So there's like a bunch of things you could do. So you could do this with like mod. So this is a shortcut way. So essentially this will give you the XOR of every number in the array. Then remember we need to XOR it with k. So XOR with k. And now our number every one in the number will be a number we needed to change or a bit we needed to change. And like I said, it doesn't really matter what number we change it in. We can change it in any bit. If it's a 1, we can change it to a 0. If it's 0, we can change it to a 1. So like it doesn't really matter where we make the change. It's possible to make that change in that bit for any number. So all we have to do is count out how many there are. So we can say 0. And then we could say while XOR does not equal 0. We want to get the last bit, so we can say if XOR and 1, which will give you, is the last bit a 1? Or like I said, you could do this as well. Either one. So if this equals 1, there's no like truthy or whatever in Java, so you have to actually check. So if this is 1, that means the last bit's a 1, and we just add result. And then we have to shift the number to the right, so you can do it like this. So you can write it a few ways. You can say XOR, so this is the shift operation, so it'll shift all digits to the right. And then here you specify how many bits you want to shift it by, so we do this. So this will just take the whole number and shift it to the right. So like I said, if we had like 4, for example, 4, then what it would do is it would shift it to the right, so this 0 would go away, and then it would look like this. It basically deletes the last bit on the right and moves everything else to the right. So you can write it like this, or you could do the shortcut again. There's also this kind of shift, which is a right error. I forgot which one is which. One of these is arithmetic, one of these is logical, but for odd, or not for odd, for positive numbers it doesn't matter. But essentially one of them preserves the left bit, so like negative numbers are written like this. So one of these shifts actually shifts to the right, but it will add a 1 over here because this is negative for negative numbers. So you can just look which one is which. You can Google that. I don't remember that off the top of my head. But for positive numbers, they both do the same thing. They're both going to add a 0 to the left. Anyway, so yeah, you could also do a shortcut operation like this. This is the same thing. So yeah, so essentially it'll get rid of the last bit, or you could do, like I said, you could do this as well. This will work. This will also get rid of the last bit, because yeah, it'll basically do the exact same thing. So but just bit shifting is generally faster, and if you're not familiar with the syntax, you can look it up and stuff like that. It's pretty simple. So essentially, once your number, until your number 0, you just keep shifting it to the right, because we want to keep getting the rightmost bit and keep checking if it's a 1. There's probably a built-in Java function as well, which you could probably look up. Like, I know there's one in Python. It's like bin or something, where you can just use it on a number and it will tell you how many 1 bits it has. But under the hood, it's basically this. So good to actually learn how stuff works. Yeah, so that's basically it, and then we just return result. Okay. So the other important thing is it is important to learn time complexity for bit shifts. So if I have a number like this, something like this, let's say I have a 32-bit number, so I have 32 of these. Worst case scenario, let's say they're like all 1s or something. To bit shift it, like, because basically what you're doing in each one of these operations is you're like deleting a number, deleting a number, deleting a number, and so on. So you're doing this 32 times. And this 32 thing, so a number might not be 32 bits, right? Like what if you had like 16 bits or something, or whatever. So basically, the number of operations it takes to check every single bit of a number is log n. Because what you're doing essentially is every time you get a bit, you divide by 2. So let's say you have, I don't know, whatever, 150. You would get a bit, you divide by 2, then divide by 2, then divide by 2. And that's basically log base 2 of n. So and anytime you want to check like every bit of a number, that's a log n operation. Yeah. So essentially the time here. So this part, and also to XOR two numbers technically is not linear time as well. It's a log operation as well, because you have to go bit by bit. So if the numbers get like pretty big, it's bit by bit. But because it's basically like for normal integers, since they're only 32, it's only like log 32, which is like basically constant time. So that's why people don't usually count it as like logarithmic or something. But you know, if your number was like some Python, I don't know, 600-bit number where like numbers don't have a finite size, I believe, it would be a lot longer. But that's why like multiplication or all that stuff counts as constant time, just because I think I forgot exactly how multiplication works, but yeah, a lot of these operations, they're referred to as constant time because it's like log of 30 or 60 or something, which is like a very small number, right? That's like 5 or whatever. So anyway, yeah, so we're going through every single number. So this is O of n. And then at the very end, we are doing this bit shift for our result. But because our result is an integer, once again, it's basically going to be like log of like 32 maximum, which is constant time. So that's why people refer to it as that, but good to know. And this works the same way with like powers and other things. Like powers is like logarithmic and things like that. So yeah, so this is just going to be O of n space. So I think this is just O of 1 because, so we have our number that we just use, and then we have our result that we just use, and that's it. So we have like two constant, or we have two variables, so that's it. And I think that's going to be it. So hopefully this is helpful. Good problem for bit manipulation, not super difficult, and especially once you do figure out like what's going on, and once you get comfortable using XORs, it definitely is pretty good for future problems. And XORs like kind of the operation with the most tricks, and if I had to pick one, it's probably the most important one to know. Probably XOR and like AND or something, but AND and OR are like very, very simple. So XOR is like the only like reasonably or like a little bit more complicated one that's also good to know. I don't think I've ever used like NAND or any of that stuff. I know how it works, but I've never run into a problem with those. But yeah, so thanks for watching. If you have any questions, as always, you can write in the comments, and I'll see you in the next one.